Welcome back to the deep dive. We're here to unpack the big ideas and breakthroughs, really cutting through the noise for you. And today, we're tackling something really fundamental. What actually allows an AI to think or reason? We all see large language models, LLMs, right? They're amazing at generating text that sounds human, super fluent. But there's this sort of persistent question, and the data seems to suggest there are real limits when it comes to deep, complex reasoning. So what if there was a totally different way? Maybe one inspired by, well, the best reasoning machine we know, the human brain. That's exactly what we're digging into today, this really interesting new AI model called the Hierarchical Reasoning Model, or HRM.
Exactly. And our mission here for you is to really unpack the research we've looked at. We want to explore how this HRM thing works, why it seems to be so efficient, and what its performance tells us. I mean, it's doing remarkably well on tough stuff like Sudoku, complex mazes, even that ARC-AGI benchmark.
Mhm.
So yeah, what does that signal about where AI might be heading? Think of this as your shortcut to understanding what could be a pretty significant leap forward.
Okay, let's get into it. So when we say reasoning in AI, what do we actually mean? It's basically the ability to figure out and execute a complex plan to reach a goal, right? Like a sequence of actions.
Mm.
And for a while, LLMs have mostly used this technique called chain of thought, COT, which is essentially like making the AI talk itself through the problem step by step.
That's a good way to put it. It externalizes the reasoning into language. But, the research actually calls it out as more of a crutch than a real solution. It forces the model to spell everything out. And the thing is, that comes with some pretty big drawbacks. For starters, it's brittle. Like, if it makes one mistake early
The
on,
whole thing can just fall apart.
precisely, it can derail the whole process. Plus, it needs a ton of training data. And because it spits out so many words, so many tokens, it's slow. You get high latency. And maybe most importantly, there's this fundamental architectural issue, the standard transformer architecture. It's described as paradoxically shallow. They aren't actually Turing complete, which means they basically hit a wall with problems needing, really deep sequential logic, the kind of algorithmic thinking needed for complex puzzles, not just pattern matching.
Wow. And you really see that in the results, don't you? Like the source mentioned these really hard tasks, Sudoku Extreme Full, 30 by 30 maze hard, and state-of-the-art tote methods just completely fail. Like 0% accuracy,
Yeah.
zero.
Yeah, and even trying to make the transformer models deeper for Sudoku didn't really fix it.
Right. It didn't lead to optimal performance, which strongly suggests, maybe just scaling up LLMs isn't the whole answer for reasoning.
Okay, so if Koki is this crutch, what's the alternative? You mentioned HRM takes a different approach. Well, the research points towards something called latent reasoning. The idea is that the real computation, the thinking, happens inside the model's hidden states and not necessarily spelled out in language. It's a big contrast to Coty. The papers emphasize that language is, a tool for communication, not the substrate of thought itself.
That makes intuitive sense. I mean, I don't narrate every single step in my head when I'm solving a problem.
Exactly. Your brain manages complex, sustained reasoning pretty efficiently without constantly translating it all into language. It just
Gotcha.
thinks, right, in this latent space.
Okay, but how do you actually build that kind of deep thinking into an AI? You mentioned just stacking layers causes problems, like vanishing gradients.
Right, naively stacking layers makes training unstable. And older recurrent networks, RNNs, they have their own issues. They often converge too early or needed this really computationally heavy training method called backpropagation through time, BPTT, which needs a lot of memory.
So where do we look?
We look to the brain. It's the ultimate blueprint, really. It solves this computational depth problem incredibly well. How? Well, a few key things. First, it's hierarchical. Different brain regions handle different levels of processing. Second, multi-timescale processing. You've got different brain areas operating at different speeds, like slow waves guiding faster ones.
Okay, like a high-level plan guiding the quick details.
Precisely. Think of it like a slow theta wave, setting the overall strategy, while faster gamma waves handle the rapid computations needed to execute it. It allows for stable, high-level control over fast, low-level stuff. Then there are recurrent feedback loops, information cycles back and forth, refining the internal representations. Higher levels guide, lower levels execute and feedback. And crucially, the brain does all this deep processing without needing anything like BPTT, avoiding that massive computational cost.
Ah, okay. And that's the inspiration for the hierarchical reasoning model, the HRM. It's trying to mimic these brain principles. So it has these two parts, right? A high-level H module for the abstract thinking and a low-level L module for the fast details, coupled together.
Exactly. Two coupled recurrent modules working in tandem. And HRM brings in some clever innovations to make this work artificially. One is called hierarchical convergence. This directly tackles that early convergence problem in standard RNNs. Basically, the L module finds a temporary solution, like a local equilibrium. Then the H module looks at that outcome, updates its own state, and gives the L module a new context, essentially restarting its computation.
So it prevents getting stuck in a rut too early?
Yes, it allows for this sequence of distinct, stable, sort of nested computations. It keeps the model actively computing over many steps, unlike older RNNs. Then there's the approximate gradient. This is how it gets around that heavy memory cost of DPTT. Instead of remembering every single step like BPTT does, which scales with time, OT memory, HRM, only needs to compute the gradient based on the very last state it reached.
Ah, so its memory need is constant, O1, regardless of how long it thinks.
Exactly. Much more efficient, and the researchers note it's also more biologically plausible.
Hmm?
Next up is deep supervision. This is inspired by how brain oscillations seem to regulate learning. HRM basically gets feedback more often during training. Each little segment of computation is treated as a step where it gets supervised, but the gradients are sort of detached between segments. This makes training much more stable.
Okay, interesting. And there was one more, ACT.
Right, Adaptive Computational Time,
Mm-hmm.
ACT. This is really cool. It's like the brain's System 1 and System 2 thinking.
Fast, automatic versus slow, deliberate thinking.
You got it. HRM learns using Q-learning, that's a reinforcement learning technique, to decide how much computational time, how many internal steps it needs for a given task. If it's an easy task, it stops thinking quickly. If it's hard, it keeps going.
So it adapts its effort.
Yeah, and the result is significant computational savings with minimal impact on performance. It only thinks as hard as necessary. Super efficient.
This is where it gets kind of mind-blowing for me. You're saying this model, inspired by the brain with these clever mechanisms, it's tiny. The research says like 27 million parameters compared to billions or trillions in LLMs.
Yeah, it's surprisingly small.
And it needs minimal training data, only 1,000 examples per task, and no pre-training or chain of thought data.
That's right. No pre-training, no COTI data needed. It learns directly from the task examples.
And despite that, it achieves exceptional performance. That seems revolutionary almost. What does that mean for building powerful AI? Maybe we don't need massive scale for certain kinds of intelligence.
It certainly challenges the prevailing bigger is always better paradigm, at least for these kinds of reasoning tasks. The efficiency gains could be enormous, and the performance numbers are really striking. Take that Sudoku Extreme 9x9 task. HRM gets nearly perfect performance. Remember, the COTI method's got 0% on this.
0. And these Sudoku puzzles are genuinely hard, right? Averaging 22 backtracks.
Yeah, significantly harder than typical Sudoku datasets. Then on Maze Hard, 30 by 30, finding the optimal path. Again, nearly perfect performance.
Okay, impressive unstructured puzzles. What about something more abstract, like that ARC challenge?
That's maybe the most compelling result. The Abstraction and Reasoning Corpus, ARC-AGI challenge, it's designed to test flexible, human-like reasoning on novel visual tasks. HRM, at 27 million parameters, hits 40.3% accuracy.
How does that compare?
It substantially surpasses leading COTI-based models, things like O3 Mini-High, which got 34.5%, and even Claude 3.7 with 8K context only managed 21.2%.
And those models are way bigger, right?
Much, much bigger. It really highlights that HRM's architecture is doing something fundamentally different, and for these tasks, arguably better than just scaling up current LLMs and relying on COTI.
And then there's that inference timescaling idea. Can you explain that again?
Sure. It means for really tough problems, like the hard Sudoku, you can just let HRM run for longer during inference when it's actually solving the problem, not during training. You just increase its computational limit, let it take more internal steps.
Without retraining it or changing the model.
Exactly. You just give it more time to think.
Yeah.
And its performance can improve further. You can leverage those extra cycles effectively. That's incredibly flexible.
But okay, is it a silver bullet? Are there things LLMs are still better at? Or is HRM just better across the board?
That's a fair question. HRM really shines on these tasks requiring deep, step-by-step algorithmic reasoning. But LLMs, especially the huge ones, have this vast world knowledge baked in from their pre-training. They excel at language fluency, summarization, creative writing, question answering based on that broad knowledge.
So different tools for different jobs, maybe.
For now, it seems that way. HRM shows incredible promise for structured reasoning and potentially complex planning, areas where LLMs struggle fundamentally. LLMs are still king for broad knowledge and language tasks, But this research definitely suggests HRM is a major step towards AI that can figure out how to think algorithmically, not just regurgitate patterns.
Okay, so it thinks differently. Can we actually see how it's thinking? What kinds of algorithms does it seem to be using inside?
That's one of the really cool parts of the research. They tried to interpret its internal process. On the maze task, for example, it looks like HRM starts by exploring several paths at once. Then it kind of prunes the bad ones, builds a rough solution, and then refines it step by step.
And for Sudoku?
There, the strategy looks a lot like depth-first search. The paper says it appears to explore potential solutions and backtracks when it hits dead ends. Pretty much how a human might tackle a hard Sudoku.
Wow. And ARC, those abstract visual puzzles.
For ARC, it's different again. It seems to make small, incremental adjustments to the puzzle board, iteratively improving it. More like a hill-climbing optimization strategy.
So it's not just one fixed algorithm.
No, that's the key. It seems to adapt, likely choosing an effective strategy for each particular task. It learns how to reason for different problem types.
That adaptability is fascinating. And it connects to something else, mentioned this neuroscience idea about brain regions and the dimensionality of their representations.
Yes. The idea is that a brain area's flexibility, its ability to handle different kinds of information or tasks, is related to the effective dimensionality of its neural activity patterns. They measure this using something called the participation ratio, or PR. Higher PR basically means the neural activity is spread out across more dimensions, giving it more capacity and flexibility. Lower PR means the activity is more constrained, maybe more specialized.
Okay, higher PR means more representational power, more flexibility. How does HRM relate?
This is where it gets really compelling. HRM shows a striking parallel to what's seen in biology, like the mouse cortex. In the cortex, PR tends to increase as you go from lower-level sensory areas to higher-level association areas.
And in HRM.
Same pattern. The low-level module state, CL, has a relatively lower PR, around 30.22, but the high-level module state, ZH, operates in a substantially larger subspace with a much higher PR, around 89.95.
Wow. So the high-level module has much higher effective dimensionality.
Exactly. And crucially, this ZH dimensionality actually grows as the model is trained on more diverse tasks, while the ZL dimensionality stays relatively stable. It suggests this emergent separation of representational capacity. The high level gets more flexible as needed.
And this isn't just built in, it learns this separation.
Yes, that's key. They checked an untrained HRM, and it showed no such separation. PR values were low and similar in both modules. So it's definitely a learned property that emerges during training.
That's incredible. Is there a quantitative comparison to the brain?
There is. The ratio of high-level PR to low-level PR in HRM is about 2.98. In the mouse cortex, that same ratio is around 2.25.
That's remarkably close.
It really is. And this finding is important because it contrasts with something called neural collapse that often happens in standard deep networks.
Neural collapse, what's that?
It's where, during training, the internal representations for different classes or concepts tend to squash together, losing their distinctiveness and reducing the overall dimensionality. It limits flexibility.
So HRM avoids that. It maintains this high-dimensional space in its higher module.
Precisely. And that high dimensionality is thought to be crucial for cognitive flexibility, for handling diverse and complex tasks. The fact that HRM develops this brain-like structure suggests it might have discovered a really fundamental organizational principle for building more generally capable AI.
Okay, so let's wrap this up. HRM, this hierarchical reasoning model, it's fundamentally a brain-inspired design. It manages to achieve really deep computation, serious reasoning power, but without the usual problems of training instability or massive inefficiency.
That's the core takeaway. It
Yeah.
really challenges the dominant approach of just scaling up non-hierarchical models like transformers.
And it offers a genuine working alternative to relying on chain of thought as a reasoning crutch.
Absolutely. The research suggests this could be a truly transformative step towards, well, universal computation and more general-purpose reasoning systems. It brings AI potentially closer to practical Turing completeness.
It's fascinating stuff. So here's a thought to leave you with. The brain uses hierarchy everywhere for almost everything we do cognitively. If looking to biology led to this kind of breakthrough with HRM, what else could we learn by taking inspiration from the brain's architecture? How might that change not just AI, but maybe even our own understanding of what intelligence is? What's the biggest implication that stands out to you from all this?